Welcome to Mech Cosmos, Engineering Explained. Right now, as you watch this video, thousands of ships are crossing the world's oceans. They carry the clothes you wear, the food you eat, the electronics you use, and almost everything else you own. The phone in your hand, the chair you are sitting on, the coffee you are drinking, almost certainly arrived on a container ship at some point in its journey from factory to your hands. Without these ships, the global economy would collapse within weeks. Supermarket shelves would empty. Factories would shut down, manufacturing would halt. The supply chains that connect every factory, farm, and consumer on Earth would simply cease to function. The modern world as we know it would grind to a halt within days, and the vessel that makes all of this possible is the container ship. Specifically, the modern ultra-large container vessel, a machine so enormous, so powerful, and so precisely engineered that it represents one of the greatest achievements in the history of naval architecture. Today, we explain everything: how a container ship is built, how it carries 24,000 steel boxes stacked 9 stories high without capsizing, how its engine produces enough power to supply electricity to a small city, how it navigates automatically across entire oceans, how the ports that receive it unload thousands of containers in under 24 hours, and how the global system that surrounds it moves more goods more efficiently than any other transportation system ever invented by human beings. We are Mech Cosmos, Engineering Explained. Let us begin. The container ship as we know it today was born from a single revolutionary idea that transformed global trade forever. Before containerization, cargo was shipped as loose goods. Individual crates, boxes, bales, and barrels that had to be manually loaded and unloaded by dock workers one piece at a time. Loading a single ship could take days or even weeks. Every item had to be individually handled, logged, and stowed in the ship's hold. Theft and damage during loading and unloading were endemic. Goods disappeared regularly from open cargo holds, and insurance costs were enormous. Labor costs consumed a huge proportion of the total shipping cost. The port time for a ship often exceeded the time actually spent at sea. The inefficiency of this system placed a significant cost on every single item of traded goods and made international trade far more expensive than it needed to be. In 1956, an American trucking entrepreneur named Malcolm McLean loaded 58 metal boxes onto a converted tanker ship in New Jersey and sailed them to Houston, Texas. This simple act launched the container revolution. The standardized steel box, the shipping container, could be loaded onto a truck, a train, or a ship using the same equipment. It could be sealed at the factory by the manufacturer and opened only at its final destination. Loading and unloading could be mechanized and automated using cranes rather than manual labor. What had taken days now took hours. What had required hundreds of dock workers now required dozens. The cost of shipping goods internationally fell by over 90% in the decades following containerization. This dramatic cost reduction was the primary driver of the explosion in global trade that created the modern interconnected world economy that we all live in today. Malcolm McLean's simple idea of the standardized box changed the world more profoundly than almost any other single engineering innovation of the 20th century. Today, the standard shipping container comes in 2 primary sizes. The 20-foot equivalent unit, TEU, is 6.1 meters long, 2.4 meters wide, and 2.6 meters tall. It is made from weathering steel that resists corrosion and can withstand both the stacking loads of containers above it and the harsh marine environment of salt spray and humidity. The 40-foot equivalent unit, FEU, is simply twice the length at 12.2 meters. A standard TEU can carry a maximum gross weight of 3,480 kilograms. Container ship capacity is measured in TEUs. The largest container ships currently in service can carry over 24,000 TEUs. If you placed all the containers from a single fully loaded ultra-large container vessel end to end, they would stretch for over 140 kilometers, roughly the distance from London to Birmingham or from New York to Philadelphia. The sheer physical scale of these vessels is almost impossible to comprehend from numbers alone. The MSC Arena, currently the world's largest container ship, is 399 meters long. That is 100 meters longer than the Empire State Building is tall. It is 61 meters wide. Its hull extends 16 meters below the waterline when fully loaded. When fully loaded, it displaces over 23,000 tons of water. Standing next to this ship at the quayside, the hull rises above you like a 9-story building and stretches to the horizon in both directions. Walking from the bow to the stern of this ship takes several minutes at a normal walking pace. The bridge, where the ship is navigated, is so far from the bow that in poor visibility conditions, the officer on watch cannot see the front of their own ship without electronic aids. The ship's crew of approximately 25 people manages this enormous machine, a testament to the extraordinary degree of automation in modern container ship design and operation. The structural engineering of the container ship hull must accommodate contradictory demands that make it one of the most challenging structural design problems in all of engineering. The hull must be stiff enough to carry the enormous weight of thousands of loaded containers without bending or flexing dangerously, but it must also be flexible enough to absorb the dynamic loads imposed by ocean waves without cracking or fatiguing. Ocean waves impose complex bending and twisting loads on the hull that vary continuously as the ship moves through the sea. The hull must be designed to withstand these fatigue loads over a service life of 25 years, during which it will make hundreds of ocean crossings through all sea conditions, from calm tropical waters to the violent storms of the North Atlantic and the Southern Ocean. A fully loaded ultra-large container vessel carries cargo weighing over 2,000 tons. The containers are stacked up to 10 high above the deck, and further stacks are carried below deck in the hold. The weight distribution changes with every cargo loading as different ports load and unload different containers at different positions in the ship. Some containers are extremely heavy, full of dense goods like machinery, metal products, or liquids. Others are very light, full of clothing, toys, or plastic goods. The ship's loading computer must carefully plan the sequence of loading and unloading at every port to ensure the ship remains structurally safe and stable at all times throughout the voyage. An incorrectly loaded container ship can suffer catastrophic structural failure at sea. The hull can literally break in two under the wrong loading conditions, combined with severe weather. Several container ships have been lost at sea in recent decades due to cargo shifting and structural failure in heavy weather, demonstrating that the engineering challenges of container ship loading remain serious and consequential. Stability is one of the most critical engineering challenges in container ship design and operation. A container ship is extremely tall relative to its beam, its width. The containers stacked high above the deck raise the center of gravity of the loaded ship significantly. The center of gravity must remain below the metacenter, a geometric point determined by the hull shape that defines the ship's initial stability. If the center of gravity rises above the metacenter, the ship becomes unstable. Any heel to one side will cause the ship to continue rolling rather than returning upright, and the ship will capsize. Container ships manage this fundamental stability challenge through two mechanisms working together. First, through careful cargo planning, dense heavy containers are loaded in the lower tiers and lighter containers in the upper tiers wherever the cargo mix allows. Second, through the use of ballast water. Large ballast tanks built into the double-bottom structure of the ship and into the wing tanks at the sides can be filled with seawater to lower the center of gravity and increase the metacentric height. The automated ballast management system continuously monitors the ship's stability as cargo is loaded and unloaded and adjusts the ballast water distribution to maintain safe stability margins at all times throughout the loading and discharging process. The propulsion system of a large container ship is the two-stroke slow-speed marine diesel engine. The engine on the largest container ships produces up to 8,000 kilowatts of power. This is enough electrical power to supply an entire city of 8,000 people. But on a container ship, this power is used entirely for propulsion. It drives a single massive propeller, typically between 9 and 10 meters in diameter, through a direct drive arrangement with no reduction gearbox between the engine crankshaft and the propeller shaft. The propeller turns at between 80 and 100 revolutions per minute, extraordinarily slow compared to any road vehicle engine. But at this size and speed, it generates the enormous thrust needed to push 23,000 tons of ship through the water at a service speed of around 23 knots, approximately 43 kilometers per hour. The fuel used by these engines is heavy fuel oil, the cheapest and least refined liquid fuel available. It is the residual product left over after all the more valuable lighter fractions have been extracted from crude oil during the refining process. At room temperature, heavy fuel oil is so thick and viscous that it barely flows. It must be heated to over 130 degrees Celsius before it becomes fluid enough to be pumped and injected into the engine. A large container ship consumes approximately 250 to 300 tons of heavy fuel oil per day at full speed. To put that in perspective, that is roughly equivalent to the fuel consumption of 10,000 family cars, all driving continuously at the same time. A single round-trip voyage from China to Northern Europe and back, approximately 4,000 kilometers, consumes around 1,000 tons of fuel, costing several $1 million at current fuel prices. The fuel cost represents the single largest operating expense for container ship operators, and every decision about speed routing and cargo loading is influenced by its effect on fuel consumption. Speed has a disproportionate and dramatic effect on fuel consumption. The relationship between speed and power required in a ship follows approximately a cubic law. Doubling the speed requires roughly 8 times the engine power and therefore 8 times the fuel consumption per unit of time. For this reason, container ship operators practice slow steaming, deliberately reducing speed significantly below the ship's design maximum to save fuel and reduce operating costs. A ship traveling at 15 knots instead of 23 knots uses roughly 50% less fuel per day. The trade-off is significantly longer voyage times. A voyage from Shanghai to Rotterdam takes approximately 30 days at 15 knots instead of 20 days at 23 knots. Optimizing the balance between speed fuel cost and the commercial penalty of late cargo delivery is one of the central operational and commercial challenges of container shipping, and a decision that shipping line operations managers make continuously based on current fuel prices, market conditions, and customer contracts. The engine room of a large container ship is a world in itself. The main engine, the two-stroke diesel, dominates the space, but it is surrounded by an array of essential auxiliary machinery. Diesel generator sets provide electrical power for all the ship's systems: navigation equipment, cargo hold, ventilation, accommodation, lighting, and the enormous power needed to operate the container refrigeration units. Approximately 10 to 20% of the containers on a typical container ship are refrigerated, reefer containers, carrying perishable cargo like food, pharmaceuticals, and flowers that must be maintained at precise temperatures throughout the entire voyage. Each reefer container has its own refrigeration unit that plugs into the ship's electrical system at connection points throughout the container stacks. Managing the electrical load of potentially thousands of reefer containers simultaneously, while also powering all other ship systems, is a significant electrical engineering challenge that requires careful load management and reserve generation capacity. Navigation of a modern container ship is highly automated and relies on an integrated suite of electronic systems working together. The ship uses GPS for continuous precise position, fixing accurate to within meters anywhere on Earth. The Electronic Chart Display and Information System, ECDIS, displays the ship's real-time position on electronic navigational charts and provides automatic alerts for potential hazards, including shallow water restricted zones, traffic separation schemes, and collision risks from other vessels detected by radar. The Automatic Identification System, AIS, continuously broadcasts the ship's identity, position, speed course, and other information to nearby vessels and to shore-based vessel traffic services, allowing collision avoidance and traffic management. The autopilot maintains the ship's course, automatically making continuous small corrections to the rudder to compensate for wind current and the directional effect of waves. On long ocean passages across the Pacific or Indian Ocean, the officer of the watch may need to make only minimal manual helm adjustments over an entire 4-hour watch. The ship essentially navigates itself under human supervision while the officer monitors all systems and maintains a proper lookout. The port operations that receive and dispatch these enormous vessels are engineering systems of comparable complexity and scale to the ships themselves. The largest container terminals in the world, in Shanghai, Singapore, Rotterdam, Los Angeles, and Port Klang, are vast, automated industrial complexes covering hundreds of hectares of reclaimed land. Modern terminals use ship-to-shore cranes that stand over 100 meters tall, with outreach of over 70 meters, to reach containers on the far side of the widest ships. These cranes can lift containers weighing up to 65 tons from the ship and place them precisely on a vehicle on the quayside in under 2 minutes. Automated stacking cranes in the terminal yard move containers between storage positions with minimal human intervention, guided by the terminal management computer system. Automated guided vehicles, driverless electric vehicles, transport containers between the ship cranes and the yard cranes following magnetic strips embedded in the terminal surface. The entire operation is coordinated by sophisticated terminal management software that tracks the position and status of every container in the terminal at all times and plans the most efficient sequence of moves to load the next vessel. A large container ship carrying 2,000 containers can be fully discharged and reloaded at a major automated terminal in under 24 hours. A logistics achievement of extraordinary complexity. The global container shipping system moves approximately 90% of all internationally traded goods by value. It is the invisible infrastructure of the modern economy, a system so efficient, so reliable, and so deeply embedded in global supply chains that most people never think about it at all. Every time you buy something that was manufactured in another country, it almost certainly traveled part of its journey packed in a steel box on a ship like the ones we have described today. The container ship is not a glamorous machine. It does not capture the imagination like a fighter jet or a Formula One car. But no other engineering achievement of the 20th century has done more to raise global living standards, reduce the cost of goods, connect the economies of the world, and lift hundreds of millions of people out of poverty than the humble standardized steel box and the enormous ships that carry it across every ocean on Earth. That is how a container ship works. We are Mech Cosmos. Engineering explained. If this video gave you a new appreciation for the invisible machine that carries the modern world, then subscribe, hit the notification bell, and join us for the next video, because every machine has a story, and we are here to tell it.